Hello, everyone. Welcome to the OpenFOAM and Combustion Simulation webinar. So today, our speaker is Professor Depeng, and he is from University of Surrey. And the title of his presentation is Numerical Simulation of Lithium-ion Battery Safety Issues, Thermal Runway and Venting and Jet Fire. So before the talk, I will first introduce Professor Kong. Professor Kong is currently a Maria Curie Research Fellow in the Fire and Explosion Modeling Group in University of Surrey in UK. Professor Kong received his PhD degree in Safety Science and Engineering from University of Science and Technology of China in 2013. And worked at China University of Petroleum, East China. So Professor Kong's current research area are dynamics and numerical modeling of lithium-ion battery thermal runway and related safety issues, poor fire behavior, and dynamics under different conditions. He has already published more than 70 journal papers in these areas. So now I give the time to Professor Kong, and also to the audience. We will have the Q&A session after the talk. So if you have any questions, you can submit through the chat function or Q&A. Okay, thanks. Professor Kong, please.
All right. Firstly, I'd like to thank Professor Zhang's invitation and provide such a good platform for us to share the recent research progress in the combustion and also OpenFOAM. Today, I'd like to present our recent research progress on the topic of numerical simulation of the lithium battery safety issues. I'd like to introduce 4 models in today's talk. The first 3 models are at the cell level. That is a model to predict the thermal runway under the local heating conditions. Also a model to predict the particle and gas venting process. That is a multi-scale model. And also a model to predict the battery fire. The final model is at battery pack or system level. That is a model to predict the gas dispersion during the thermal runway propagation. As we know, the lithium battery now are widely used in our daily life. For example, in our life, we use the cell phone, our cell phone, laptop, and other electronic devices use the lithium battery for the power. In order to achieve the goal of the net zero carbon, many countries like UK, USA, and China are promoting the sales and productions of the electric vehicles. From the left figure, we can see that from 2014, there is a quick increase of the market share of the electric vehicles in the world. In addition to the field of the electric vehicles, the lithium battery are also widely used in the field of the electrochemical energy storage. The right figure shows that from the right figure, we can see there are more than 19% of the electrochemical energy storage coverage of the net zero carbon. However, the safety issues related to the lithium battery is an important part that we cannot ignore. For example, there are some fire and explosion accidents occurred from time to time. Here we give some examples. For example, for the very famous electrical vehicle brand Tesla, the Model S got fired when it was plugged in a supercharger station, and the Model S was totally destroyed during the fire. Another accident occurred in Australia in an energy storage station, because the energy storage station usually use a lot of lithium batteries, so the fire is very large and lasted about 4 days and 4 nights. it was in a condition, in an abused condition. For example, if for example, the battery is in addition of the mechanical damage or the overheating or overcharge, then they will generate more heat than they can dissipate. As a result, the heat will accumulate and lead some runway. Usually, if the lithium battery occurred some runway, they usually experience the process of gas generation, venting, and also the jet fire after the summer runway. So for the venting of the fire behaviors, there are two characteristics. First one is during the venting process, they will release a large amount of combustible components such as hydrogen, CO, methane, and electrolyte vapor. For the fire behaviors, they will release a large amount of the heat from the electrochemical reactions and also the combustions. Usually, the battery are used in the form of the battery pack or battery module. So the heat radiation from the fire will usually accelerate the thermal runaway propagation in the battery pack, and also the flame of the fire can ignite other components of the pack to make a more severe consequence. In order to prevent the fire, we have to understand the mechanism of the thermal runaway and fires. There are two ways for this goal. First one, we can do some experiments. But for the thermal runaway experiments, they are very expensive, and also the experiments are usually dangerous to the operators. So it is necessary to develop some model numerical model to replace the dangerous and also expensive thermal runaway test. In order to achieve this goal, we have developed some models to predict the thermal runaway behaviors and also the related safety issues. This model covers from the micro scale, that is mainly about heat and gas generation, to the cell scale, that is to predict the thermal runaway behaviors and also the jet fire and also the venting process. Then we also extend our model to the module scale or even the system scale to predict the gas dispersion process. Okay, now let's see the first model, that is to predict the thermal runaway under the local heating conditions. As we know, the thermal abuse is one of the most direct factors. Heating is very most common. However, in the previous work, they usually put focus on the oven tests that represented the condition to a high ambient temperature, and the temperature distribution is uniform. In our work, we use the frame of OpenFOAM to develop a thermal runaway model to predict the thermal runaway behaviors on the local heating. And we also use this model to investigate the influence of different factors, such as the heat generation, external heating, and also the heat dissipation conditions. Here is the model framework. In this model, we use the three-dimension energy conversion equations to get the temperature field for the battery. And we also use the LAMP model, that is a Arrhenius equation, to describe the exothermic reactions inside of the battery. Because for the thermal runaway of the battery cell, the main source of the heat generation is from the reactions among the battery materials. Here we consider the 6 reactions, that is the decomposition of the SCI layer and also the electrolyte decomposition. We also consider the reactions among the battery materials, such as anode, cathode, and also the electrolysis, and also the boundary reaction, as well as the separator melting process. Before we use the model to predict some, before we use the model to make some new simulations, we also made some tests to validate this model. Here we use 3 different kinds of the cells for the validation. The first, that is the LCO cell, NCE cell, and also the LFP cell. From the results, we can see that our model can make a good prediction of the peak temperature and also the onset time of the thermal runway. After the validation, we use the model to make some investigation of the influence of different factors on the thermal runway behavior. The first factor we considered is the battery materials. Here we define 2 indicators to characterize the thermal runway behavior. First one is the thermal stability, that is the onset time of the thermal runway. The other one is the thermal safety, that is refers to the peak temperature of the thermal runway. From the results, we can find that the LTO nodes show the better thermal safety and stability than the graphite anodes. For the cathode materials, the LFP shows the best thermal safety and thermal stability. The simulation results also, we can also find from the results that if we increase the melting point of the separator, then the thermal stability of the battery can be improved. The results also suggest that for the electrolytes, it shows limited effects on the thermal safety and the thermal stability. The second factor we considered is the low heating conditions, heating positions. Here we consider 3 different heating positions, that is heating as on the middle and also on the end and also on the bottom of the battery. The results reveal that the thermal runway occurrence probability will be higher if we hit the battery near the bottom. The reason may be due to the uneven temperature distribution, because it causes poor heat dissipation. The last factor, the heat dissipation conditions, is very important for improve the safety of the battery. Here we consider 2 measures for the heat dissipation conditions. First one is the air speed. Another one is the ambient temperature. From the results, we found that if we increase the air speed or reduce the ambient temperature, both of them can delay the onset time of the thermal runway. If the air speed is large enough or the ambient temperature difference large enough, these 2 measures even can inhibit the thermal runway. However, both of them have little influence on reducing the peak temperature. So both of them are only effective to improve the thermal stability. The second model is about to predict the particle and gas weighting during the thermal runway. As we know, during the thermal runway, the venting process is very important. During the venting process, some combustible gases such as hydrogen, CO, and methane will be released from the broken safety valve. In addition to the combustible gases, actually some solid particles such as the melting gases, because the solid particles are usually has a very higher temperature and also has a very higher velocity. So these solid particles may serve as a medium for igniting the gases and lead a fire propagation. However, in the previous study about the venting process, they usually considered the gas venting and need to focus on the solid particle venting process. In our work, we have proposed a multi-scale model for the gas and particle venting process. And this model can reveal the complete evolution from the for the ejected particles from its generation, jet, spread, and to the final deposition, the whole process. Before we develop the mechanism of the lithium battery venting process, actually the venting process is very complex. It is a combined action of the chemical reactions and also the physical transformation. Here, we divide 3 regions for the simulation. That is the jelly root. That is the jelly root inside of the battery, and also the phase change and headspace region. It is also inside of the battery. It's above the jelly root region, and also the ambient fluid. It is outside the battery. Then we consider the 3 levels for the modeling. For the battery scale, we use a LAMP model to predict the thermal runway and jet dynamics parameters. At the chamber scale, we use a CFD model to predict the flow fluid evolution outside the battery. And we also use a DPM model at the particle scale to predict the solid particle jet spread and sedimentation process. Okay, let's see the modeling at the general region. In this region, the main contribution for the venting and thermal runway process is it will generate heat and gas during this region. So we use the Arrhenius equation to describe the thermal runway progress. In addition to the heat generation, this process also generates some gases. In order metrics to describe the gas generation for every reactions. For the phase interface and headspace region, there are 2 factors. There are 2 processes that we have to pick. The first one is the propagation, and also the particle entry. For the electrolytes, they consider the change into phase. The first one is the reaction conduction, and the other one is the electrolyte vaporization process. For the solid particle increment, for the solid particle increment, we consider this process as gases carry the solid particles during the cell venting. After the particle and gas ejected out of the battery, then we have to consider the change of the pressure and the venting process. So we use the ordinary differential equations to calculate the pressure and the jet dynamic parameters change. For the ambient regions, we usually consider the gas flow and the particle transport. For the gas phase model, we use the CFD model and based on the FBM methods to predict the gas flow fluid. And for the solid phase, for the particles, we use a DPM model to predict the motion trajectory of the particles. We also made some tests to validate our model. Here we use the PRS to visualize the ejected particles and gas flow. And we also measured the mass loss and jet velocity by the electronic balance and pit torch tube. In addition to these measures, in addition to these measurements, we also use the SEM to observe the surface of the particles and made a statistical analysis for the size distribution of the solid particles. And we found that there are two peaks for the size distribution. Then we use the log normal distribution functions to fit the particle size, and the fitted function was used as the input of the model. Here is the simulation and boundary conditions for for our model. Then we compared the results from the tests and also from the simulation. From the results, we can see that the predicted cell temperature and also the jet velocity are consistent with the test results. In addition to this, this model can also identify two velocity peaks that is occurred at the safety valve opening and also the thermal runway progress. This model can also review the mass loss evolution. And from the results, we found that the solid particles and the electrolyte vapor is the main venting materials of the battery jet. And from the results, we can also find that the major gas release during the venting is different. Before the thermal runway, the main component is the electrolyte vapor, and during the thermal runway, that is the generated gas due to the reactions. We also compared the jet geometry characteristics, and we compared the angle of the jet and also the radius of the jet. From the comparison, we found that the predicted angle and the radius is consistent with the experimental results. This model can also use to predict the spread and the decomposition of the generated particles. And we also use this model to investigate the influence of the ventilation on the particle mass. So from the above introduction, we can see that the proposed model can reveal the entire chain of the venting phenomena, that is from the jet spread and to the final deposition. The third model we developed is about a model to predict the jet fire of the battery. As we know, the battery fire is very different from the hydrocarbon fuel fire, because during the currents of the fire, they're usually related to the internal electrochemical reactions inside of the battery, and also outside the battery there is also a flow field. So if we want to model the battery fire, we have to couple the internal electrochemical reactions with the external flow field. Here we developed a model based on the solid and fluid heat transfer. This model includes some models. First one is the thermal runway models. That is use a series of the Arrhenius equation to predict the thermal runway. And also we use some ODE, that is ordinary differential equation, to predict the pressure and the venting process. For the outside of the battery, we use the runs model to describe the turbulence process, and use the EDC model to describe the combustion. And in order to couple these above models, we use dynamic boundary conditions to accompany these models. We also use this model to make a simulation for a cylinder NCA cells. And before do the simulation, we also made some validation experiment for the NCA cylinder cells. Here is the compared results from the tests and also the simulation. From the results, we can find that the model can predict the peak temperature and onset time of the thermal runway very well. And also, this model can capture the fluid temperature rise above the battery during the venting and the thermal runway process. We also compared the flame geometry. From the video, we can find that the model can predict the flame height and also the flame shape very well, which is in line with the experiment. And also, we use the model to study the influence of the SOC on the fire parameters such as the heat release rate and flame height, and found that the SOC plays an important role for the fire parameters. Okay, these three models are at the cell level, and let's see the last model. That is a model at the system level. As we know, in the practical application, the battery are usually used in the form of the battery pack or battery module. If one battery occurred on thermal runway, the thermal runway may propagate from one cell to another cell. During the thermal runway propagation, that will generate a lot of the combustible gas. As a result, the gas will accumulate and get a gas dispersion, even explosion in the confined or semi-confined space. For example, in 2021, there is an explosion accident occurred in energy storage station in Beijing. So it is very important to link or to predict the gas dispersion behavior during the thermal runway propagation. To develop this model, I think there are two challenges. The first one is how to couple the thermal runway propagation with the venting process. The second one is how to make a balance of the model accuracy and the calculation time, because we can use the CFD models to predict, to simulate the thermal runway behaviors totally, but it requires a very higher computational resources. But in the practical application, it is not feasible. So we have to make a balance between the accuracy and the effectiveness. Here we developed a model that is a CFD model coupled with the lumped thermal resistance network. This is the framework of the model. In this model, we considered the battery as a node, and then this node are collected according to the battery arrangement. For the heat transfer, we considered three ways for the heat transfer. That is the heat conduction, between the heat conductions between battery and a wall, and also the convections between air and the batteries. The thermal resistance network are used to predict the sequence of the thermal runway propagation. For the gas dispersion process, we use a CFD model to predict it, and also we also calculate the lower explosion limit for the venting gas mixture to determine the explosion risk for the gas. We also made some model validation, and here we compared the concentration of the of some gases such as hydrogen, CO2, CO, and methane. From the results, we can see that the concentration of these gases are in line with the measurement. And also we found that this model can predict the thermal runaway propagation very well, because we found the predicted peak temperature and the onset time of the thermal runaway for each cell are very close to the measured values. We also compared the calculation efficiency. Here we compared the calculation. We use the same scenario by two ways. The first one is the CFD plus the TRA model, and also we use the complete CFD model to predict the same scenario. From the results, we can see that for the CFD plus the TRA model, it can reduce the grid points, and correspondingly, the calculation time is shortened greatly. Then we use the model to investigate different factors, the effects of different factors on the gas diffusion behavior. For example, we investigate the void volume on the gas diffusion behavior. And from the simulation results, we can find that the model can capture the sequential venting behavior during the thermal runaway propagation. And from the results, we can also find the periodic evolution of gas concentrations. And the reason may lie in the discontinuous of the venting process. And also we found that the void volumes of the battery pack on the explosion risk after the thermal runaway. Also, as we mentioned before, this model can make a good balance of the accuracy and the communication and the effectiveness. So we can extend this model to a more larger scale. That is, for example, as shown in the animation, it is gas dispersion in a energy storage station. So this model can be used to evaluate the gas explosion risk for the energy storage station. Okay, the final part is the summary. This is the conclusion from the talk. I will not repeat it again. For the future work, I think we will put a focus on we should understand the gas generation mechanism. The second one is to understand more, to incorporate more physical fields in the modeling to make a more realistic thermal runaway behavior prediction. Here, I also want to show my thanks to the financial support from the Horizon 2020 and also the NSFC for their financial support for our research work. Okay, this ends of my presentation. Thanks.
Okay, thank you very much, Professor Kong, for your very nice talk. And so in the following, we will move to the Q&A session. Okay, so now we have questions from the audience, and I will raise a question for you. Okay.
All right.
Yeah. So the question is, in the context of dealing with thermal runaway inside a battery pack, from both experiments or numerical modeling perspective, what do you think we can do to identify a cell failure before thermal runway even happens? This first. And second is there any physical behavior we can use as indicator for that? So 2 questions.
All right, thanks for the question. I think this a very good question because from my point of view, I think these 2 questions actually related to how to make an early warning about the thermal runaway. Because if the thermal runaway has occurred, actually we have little work can do to prevent it. So for the thermal runaway, the most important the most important is how to identify some parameters or some signals to characterize the thermal runaway. I think we can measure the monitor the parameters like the temperature and also the voltage, current, and also some gases to predict the thermal runaway. Is that okay for this question?
Yes, I think so, because the audience cannot speak. Okay, so if the audience have any further question, can submit again. Okay, yeah. And for the second one, is there any physical behavior we can use as indicator for that? So do you have any comments or suggestions for the second question?
Yes, as I mentioned, we can use the the current, the voltage, and as the indicators for predict the thermal runaway occurrence.
Okay.
And also we also made some tests to monitor the force, because usually if there is a thermal runaway before the thermal runaway, they will generate some gas, and the gas will make a will make a shape change of the battery, and correspondingly there will be a force change during the shape change. So we may monitor the force change during the for the battery as an indicator for thermal runaway. Yeah.
Okay. Thanks. So any questions? Any further questions from the audience or the panelists? For the panelists, if you have questions, you can unmute yourself and ask directly to Professor Kong. Okay. Yeah, so perhaps I ask one question. So normally, you know, for thermal runaway, different factors actually you can induce this hazard, right? So in our modeling, how did you model the thermal runaway like factors like short circuit or others?
Right. In our current models, we only put a focus on the overheating. Maybe you can find it. Yeah. Yeah. Here we consider the the thermal runaway. The trigger for the thermal runaway is overheating. Then we made some experiment by some heating tests, such as use the arc test, get the heat flow and also the heat flow, and then we can get the dynamic the parameter like the A and also the E from the reactions. Then we get the parameter, we get the values of the reactions. Then we put these values into the reaction equations, and by this way we can predict the thermal runaway behaviors under the overheating conditions.
Okay. Okay. Thanks. Yeah. So any other questions? And in this modeling, in this work, in your work, and also in majority of the work published in the literature, so for thermal runaway, normally we use several steps, right, to describe the entire thermal runaway process, right? So what is your opinion, actually, if we need a more detailed model, or let's say a mechanism, somehow like a chemical mechanism to describe the thermal runaway process, if we would like to understand the more information behind this hazard?
Yes, actually, as you mentioned, in our model, there is a simplification for the electrochemical reactions. We already considered we use the Arrhenius equation as shown in these slides to describe the reactions. But in fact, the reaction may be more complex. So if we want to, maybe we can make a further study about the reactions, the chemical reactions during the thermal runaway process. But in our research, we only simply characterize them by the Arrhenius equations. Yeah.
Okay, thank you. And one more question from audience. Dear Professor, Professor Kong, how can we make sure the thermal runaway temperature in the thermal runaway model? Yeah. So
How
this
to make sure the thermal runaway temperature is for the test, we usually use the thermocouple to attach the battery to get the temperature change. And for the modeling, because we usually this equation to get the temperature change. So by this equation, we can get the temperature field. Then we can get the temperature change, like this. Yeah.
Okay. Yeah. Okay. Thanks. Any other questions?
Hi, Huang. Maybe I can just throw in a quick questions for Depeng. Thank you for the nice presentation. Actually, it's a very admirable work. I'm just curious, in terms of a practical standpoint. So I want to hear from you, because let's say like I want to complicate the simulations. I want to include like structural models in the deformations of the battery during the whole process of the thermal runaway and bursting into flame. As well as just now you mentioned the possibilities of bringing in more complex chemistry. I guess my question is, your results seems to be very good already. So like in practical standpoint, is there really a purpose of a point for us to go through making the simulations more complicated? What are the added values that we can get out of this?
So sorry, maybe I didn't follow your question. Can you repeat again?
I mean, like, so we can, of course, add in more things to complicate the simulations, like the structural models to capture deformations of the batteries, or just now you were talking about complex chemistry as well. But my point is, your results looks very good already, at least from what I'm seeing in all your some of your publications and the work that you're presenting here. So from your opinions, like what would be the added values for us to run really high fidelity simulations, or some things that captures more of the physics, and what are the added benefits that you can imagine?
Actually, for the battery thermal runaway, I think it is there is some random for occurrence. So in our research, actually we do some experiments, and also we do some repeated tests we repeat some tests to get the results and compared. For the future, maybe there is also some new materials for the battery, and I think we make how to say. In addition to the battery materials, maybe also some abuse conditions also have influence on the thermal runaway behaviors. So in the future, maybe we will put a focus on different build condition simulations. Yeah.
Okay. Thanks.
Okay. Yeah, Wally, thanks. Any other questions? Oh, there's one question from the Q&A. The audience is asking, instead of OpenFOAM, is there any commercial software can be used for thermal runway? Yeah.
Yes, there are some software, commercial software for predicting thermal runway, such as Combustion, and also maybe we can use the front to predict the thermal runway. But the problem is most of them are not used specifically for the thermal runway prediction. And as I mentioned, for the battery thermal runway, it is a very complex. Maybe, for example, for the battery fire, we have to consider the inside electrochemical reactions and also the combustion process. So the commercial software maybe cannot simulate the battery fire very well. So that's why we want to develop some models in the OpenFOAM to predict the thermal runway venting and fire. Yeah.
Okay. Yeah. Thanks. Any other questions from the? Oh, okay. We have one more. Okay. So the question here is, how did you model the generation of solid particle during the thermal runway process? Yeah, this is the question from the audience.
Yeah. For this question, actually, we determined the soft particles based on the literature, and we determined some particles have occurred during the process and didn't consider the generation of the solid particles. So we just simulate the particle jet and also is spread outside the battery. We didn't consider the generation of the solid particles. Yeah.
Okay. Yeah. Thanks. So actually, a follow-up question, because here we are talking about gas venting, right? So normally, the gas composition from the battery probably will be very different, right? Consider, when we have different like battery material and also SOC and so on, right? So in the modeling, how did you determine the gas composition? This is one. Another one is once we have a mixture of different fields in the vent gas, right? So how can we determine a good chemical mechanism to model the combustion process of the venting gas?
Yeah, that's a very good question. And yes, we agree with your comment. Yeah, there will be different gas composition for different chemical system. But we can also find some studies about the gas composition in the existing literature. So in our work, we get the composition from the literature. Then we use this composition as an input for our model. Also, yes, if we continue to do this work, we may have to understand the mechanism of the gas generation for different chemical system for the battery. Yeah.
Okay. Yeah. Okay. Thank you very much. Any other questions from? Okay, we have one more question. So from the same audience, Professor Kong, how to model the size and mass flow rate of solid particles?
For the particle size, we actually here, as we mentioned, as shown in these slides, we make a statistical analysis of the size distribution, and then we made a fitting. We made we use the log norm distribution to fit the distribution, and then we put the distribution function as the input for the model. And for the eject, we actually use this here. We use this equation to model the solid mass loss, and use the DPM model to predict the motion trajectory of the particles movement. Yeah.
Okay. Yeah. Thank you. Thanks. Any other questions? Okay. Seems no more questions. Okay. So if no more questions, and we thank Professor Kong again, and for the very nice talk, and so I encourage every panelist open your camera and say bye to each other. Okay.
Okay. Thanks, Professor Zhang. Okay. Say.
Yeah. Okay.
Bye.
Yeah. Bye bye. Thank you. Bye bye. Yes.
Bye.
Bye. Yeah. Bye bye. Bye bye. Very bye.
Bye. Bye. Bye. Bye.
Bye.